Okay. Today we are going to talk about angles and directions. This is the assignment for this week in class, is to go through and learn about Chapter 4, Angles and Directions. There are two types of angles that we address in this course: vertical angles and horizontal angles. Surveyors measure both vertical and horizontal angles. Horizontal angles, though, are what we need to determine both azimuths and bearings, and we'll see a little bit later on what those are. And we know from the course that angles are always measured in degrees, minutes, and seconds format. Okay? In order to measure an angle, you need a reference or starting line, right? You need a point of reference to start with, and you need a direction of turning. As we saw in the lab on Friday, the standard is to turn our angles to the right, and then that gives us the angular distance or the value of that angle. Here's an image to talk about vertical angles. In a lab, I don't know, 3 weeks ago now, I believe it was, we did slope measurements, and we used the zenith or vertical angle in order to determine the trigonometric relationship to calculate our elevation. So you can see here from the diagram that, let's get my pen going here. Okay. You can see from this diagram that your zenith angle here is measured from directly overhead, right? So here's your instrument, and you're measuring downward to whatever point you're measuring to. Your nadir angle is measured from that same vertical line, but in the opposite direction, heading upward. And then your vertical angle is simply defined as a positive or negative vertical angle off your horizontal. So positive vertical angles, negative vertical angles going that direction. Okay. Forgot the mouse doesn't work anymore. Okay. Meridians. Meridians provide a sense of direction. So the horizontal angle between the line and an arbitrarily chosen reference line, which is called the meridian, is how we define horizontal angles. There are multiple types. There are geographic meridians. These are lines on the mean surface of the Earth joining north and south poles. Okay? Those are called meridians. All lines of longitude are meridians. They're geographic meridians, also sometimes referred to as geodetic, and they are fixed. They are unchangeable. Lines of longitude are what they are. We can't change them. There are magnetic meridians. These are parallel to the directions taken by freely moving magnetized needles, as in a compass. So a compass can provide you magnetic north, and magnetic north could be a meridian that you use to measure from. But magnetic meridians vary with time and location because magnetic fields vary across the Earth. You can have a grid meridian. These are meridians that are referenced to a grid on the ground. These are based on state plane coordinate systems, which you will learn about in 102. You can have an astronomic meridian, which is very similar to a geodetic or graphic meridian, except that instead of using, for example, a line of longitude, you are actually deriving observations from space, and therefore they're astronomic. You can have a meridian of record. This means that it's the meridian that's defined in the field book by the surveyors at the time that they took the measurements. And you can have an assumed meridian, which is typically what we'll be using in this class, which is we're just going to identify that that line right over there is our meridian. It's not officially any other type of official meridian. It's not a geographic, a magnetic. We're not using the stars to get it. We're just saying that line over there is where we're starting. And that line over there is assumed to be north. So those are options as well. Horizontal angles. There are three types of horizontal angles. There are interior angles, which are those angles measured on the interior of a closed polygon. We would call that a closed traverse. There are exterior angles, which are all of the angles measured on the outside of a closed polygon. And if you recall, for interior angles, n-2 times 180 degrees will give you the sum of the angles inside of a polygon. So that's for interior. Exterior angles, n+2 times 180 degrees will tell you the sum of all of the angles on the exterior of a closed polygon. Then we have deflection angles, which by definition are measured from an extension of the back line to the forward station. They can be measured to the right or to the left, and clockwise to the right is considered positive. That's clockwise to the right, and negative is counterclockwise. Which is left. Okay? And deflection angles are, by definition, always less than 180 degrees. It is the angle between the preceding line and the present one. And we'll see a diagram of that in just a minute, which hopefully will help a little bit. Okay, moving forward. A closed traverse. You guys have already measured a closed traverse in your lab. You did that on Friday. And here's just another example. By definition, a traverse is a series of connected lines whose lengths and angles at the junction points have been measured. We just talked about interior angles, which would be, come on, which would be these angles here, right, measured on the inside of the polygon. And then here's an example. Here's an example of an exterior angle. Okay? And each and every one of these angle points has both an interior and an exterior angle. Here we go. So in this example, the interior angles of our closed traverse equal 540 degrees. But as you could see from your field exercise, it's not typical that you end up exactly on the dot for measuring your interior angles. An open traverse is what we see when we talk about deflection angles. So as we said, the definition of a deflection angle is an extension of the back line to the front line, to your forward station. So 0 plus 0, 0 back here is where we started. Our instrument is sitting here at station 1 plus 4326. We sight back here. You're going to flip the gun over, so you're now pointing in this direction. And then you're going to turn either to the left or to the right and sight on your next point, which is here at 3 plus 7127. The angle that you turn, in this case 22 degrees, 18 minutes, right is your deflection angle. And this right or left is extremely important because otherwise you wouldn't know which direction the 22 degrees was going. Then you would pick up your instrument. You're now going to occupy 3 plus 7127. You're going to sight back to your previous station, your previous point. You're going to flip the gun, which now has you pointing the opposite direction. And as you can see here, you're then turning to the left to sight on your next point, 38 degrees, 6 minutes left. These are deflection angles, and we will be doing a deflection angle lab, I believe, at our next lab meeting. So you will get a chance to practice this in the field. And these deflection angles are typically used for a route survey of some kind, a highway, a train, something like that. The downside to doing an open traverse and using deflection angles is that it is very difficult to check your work. In a closed traverse, you can compare the geometry mathematically, and then you know whether or not you're right on target. Here, it is much more difficult to do that. So let's move on and talk about directions. We can measure angles all day, right? We can find a starting point, find an ending point, and measure the angle between those 2 points horizontally. But what's really important about our angle measurement in surveying is direction. It tends to tell us where we're headed. So we have what are called azimuths and bearings, and these define the direction of those angles. Azimuths, let me get a darker blue back in here, okay? Azimuths are horizontal angles measured in a clockwise direction from any reference meridian. So they are typically measured from north. So here's our north meridian. And they range from 0 to 360 degrees. So an azimuth will always be measured, it's kind of a bad looking arrow, there we go, from north, which is both 0 degrees and 360 degrees. So our azimuth will be measured from north in a clockwise direction anywhere between 0 and 360 degrees. Okay? This would be south, this would be east, this is west. Therefore, due east is 90 degrees, due south is 180 degrees, and due west is 270 degrees. Does that make sense to everybody following along here? Awesome. Yay. Okay, so that is our definition of an azimuth. Our definition of a bearing is a little bit different in that it is the smallest angle which a line makes with a reference meridian. Okay? Sounds a little bit more confusing. When we have a bearing, we will always measure a bearing from north or from south. So bearings, by definition, will always be less than 90 degrees. They will be measured from south to east, from south to west, from north to east, or from north to west. So you always have a reading less than 90 degrees. Okay, let's look at some examples. Azimuths. Here's our line, 0 to 1. It is 52 degrees from our north meridian. What is the azimuth of this line? Remember our definition that azimuths are always measured from north in a clockwise direction and may have value from 0 degrees to 360 degrees. So what would be the value of the azimuth of line 0 to 1? Yes, 52 degrees, exactly. So if we look at the line 0 to 2, what is this right there? This azimuth of the line 0 to 2. Well, we know that to here is 90 degrees, correct? From north to east is 90, so this initial portion is 90 degrees. What we need to know is what this little bit is right there. Yes, 180 minus 59. Okay, Josh, this is not 89 degrees, right? The azimuth of line 0 to 2 is going to be equal to 90 degrees plus this amount here. Yes, 90 plus 90 minus 59 degrees, exactly, which is 121 degrees. So the azimuth of line 0 to 2 is equal to 121 degrees. Okay? How about we look at line 0, 3? Does that make sense, Josh? Are you following with me? Okay. So now we're looking here at line, use another color before it gets too busy, of line 0 to 3 right here. So we know that up to this point we're at 180. Yes, plus the 22 gives us 202 degrees. That's our azimuth of 0 to 3. Okay? And then if we look at 0 to 4, the azimuth of 0 to 4 yes, it's 360 degrees minus 35 degrees will give you this line right here, which is the azimuth of line 0, 4. So that's how we define our azimuths, and that's how we calculate them. And very often, much as we had to here with line 0 to 2, you have to kind of be a little bit of a detective and really look at the information that you have and the information that you need to figure it out. Okay, bearings. Remember, bearings are measured from north or from south to east or to the west. So if we are looking at line 0, 5, what is the bearing of line 0, 5? Well, we start at the north, we start reading north, and we're heading to east. How far are we heading? 58 degrees, 20 minutes, 58 degrees, 20 minutes east. That is our bearing of line 0, 5. Now, whenever you write a bearing, you must include your directional component. Okay, so let's look at 0 to 6 here. What is the bearing of line 0, 6? Yes, I'm aware. Thank you, Sandy, but the answers are on the table. Okay, Josh, you're really, really close. You always start, remember that you always start with north or south. Your first letter will always be north or south. So you're measuring from south to east. So we're going to be south. Now how many degrees? This is what we need to figure out. Well, we know that we're in a quadrant here of 90. So 90 minus 65 degrees, 10 minutes, is 24 degrees, 50 minutes east. Okay? Let's look at the southwest quadrant. Well, let's look at 0 to 7. I'll change my pen color again so we don't get too much on here. So we're looking at 0 to 7. What is the bearing of line 0 to 7? We start south. That looks more like an S. We're heading west. How far west? 90 degrees minus 62 degrees, 30 minutes. 27 degrees, 30 minutes west. Everybody following what we're doing here? Could you ever use a different bearing that would give you an angle greater than 90 degrees? No, because if you had a line that now encroached on another sector here, another quadrant, like that moved up here, you'd now be measuring from north instead of from south. So if you're doing a calculation and your bearing comes out to be larger than 90 degrees, then you know that you're actually in the other quadrant, you know, and you're not where you think you are. So by definition, a bearing must be less than 90 degrees. Well, it must be 90 degrees or less. Okay, so if we look at our last line here, 0 to 8, what is the bearing of line 0 to 8? Again, we have to start with either north or south. We're starting with north. And we're heading west. How far west? 10 degrees, 45 minutes west. There's your bearing for line 0 to 8. Okay, seems simple enough, right? Moving on. Let me back up a second. The intent of these azimuths and bearings is, again, direction. So if you know that this line here is your meridian, right, your starting point, your known reference point, if someone were to tell you to put in a line at an azimuth of 52 degrees, you would know exactly where you were headed. You would know that you are somewhere on this line here, because you know where your meridian is and you can mark off 52 degrees and you know that you're heading in that direction. It is like coordinates. It's a manner, I guess you could compare it to coordinates. But it's all about direction, directionality. So once you know where your meridian is, when someone gives you an azimuth, they're actually telling you what direction you're headed. So an azimuth of 202 degrees from this same meridian puts you down here heading in this direction, right? So bearings, it's the same thing. If somebody, If somebody tells you to mark off at a line at a bearing of north 58 degrees, 20 minutes east, and you know this to be your meridian, then you know that your line is heading in this direction. So these bearings and azimuths are all about direction, the direction of travel, the direction that you're heading. Having said that, there is now what's called reverse azimuths. So if you're heading, and reverse bearings. So if you're heading in one direction, if you make a 180-degree turn, you are now heading the opposite direction back down the same line. So if I started out heading north 58 degrees 20 minutes east, I'm heading along this 0 to 5 line. If I stop here and turn around 180 degrees in either direction, then I'm now heading back down the same line in the opposite direction, right? I'd be heading like this in the opposite direction. That is called a reverse bearing or a reverse azimuth. So in this example, let me put a darker color back up here. So in this example, here's our meridian, our north meridian, right there. Here's our line, C to D, and here's our azimuth, 128 degrees, 20 minutes. There, right there. There's our azimuth. So if we traveled from point C to point D, and then we wanted to turn around and travel back from point D to point C, what would the azimuth be? Well, here's that same meridian. Notice it's parallel. This meridian right here and this meridian right here are the same meridian. They're parallel. So to go from here and then back, we had to travel. So here, let me just draw this little extension. I wish it were straighter. Should be. So there's your C to D direction, right? You are turning 180 degrees. Here's that 180 degrees right there. There's your 180, in order to head back down that line in the opposite direction. So therefore, the azimuth of line D to C is equal to the azimuth of line C to D, 128 degrees, 20 minutes, plus 180 degrees, which gives you 308 degrees, 20 minutes. So this line here, make that a different color. So this line right here represents the azimuth of B to C, and it is 308 degrees, 20 minutes. So with azimuths and reverse azimuths, they're always going to be off by 180 degrees, right? If you're standing on a line and walking one direction, you have to turn 180 degrees to travel in the opposite direction back up or down the line. And it doesn't really matter whether you turn to the left or you turn to the right. It makes a little bit of difference in the math. If you were to turn to the left, you would have had to subtract 180 degrees from 128 degrees, which would actually bring you back to this point here, this direction. But now you'd be at a negative amount of degrees, and then you'd have to subtract that from 360 to get the forward amount of degrees. So typically, if your azimuth is less than 180 degrees, you add 180 to get the reverse azimuth. If it is greater than 180 degrees, you subtract it to get the reverse azimuth. That keeps the math a little bit simpler. Still with me? Does that make sense? Okay, we can do very similar things with bearings. The nice part about bearings is that the actual value of the angle never changes. Due to our geometry, when you have two parallel lines, the line connected in between, this angle and this angle are always the same. And then this angle and this angle are the same. But our bearings are always measured from north or from south. So, by our definition, the bearing of line A to B, remember direction is important, so the bearing of line A to B is north, 62 degrees, 30 minutes east, right? Because if we dropped in here, this would be east. Now we want to head back down that same line in the opposite direction. That actually should have been drawn just a little higher. There we go. At that junction point. Now if we wanted to travel in the opposite direction down the line, so from this way back down to this way, we now would be measuring from south 68 degrees. And I can draw this in here. And we're now heading southwest. Yes, alternating angles. So it's very easy reversing bearings because you simply reverse the direction. So north becomes south, east becomes west. They're very easy to do. So where is all of this taking us? Well, let's look at a couple examples really quick. Oh, wait. Oh, here we go. Here's where all of this is taking us. We need to be able to convert back and forth between azimuths and bearings. So we need to take an azimuth and convert it to a bearing, and we need to take a bearing and convert it to an azimuth. Your book is lovely and provides these little formulas, if you will, or little explanations on how to do those calculations. But I would say you don't need to remember these things here. If you simply look at the diagram, this becomes evident. Bearings to azimuths, here's the little rules if you want. But again, when we look at them on the diagram, it becomes evident how to convert a bearing to an azimuth. So let's go back here and look real quick. So here is our diagram. Here's our north, our south. So you can see what I'm talking about, east and west. Let's go back to a darker color. So if I have a line here going in that direction, my azimuth by definition is this angle here. Let's call it 60 degrees. So we know what the azimuth is. What's the bearing of that angle? It's equal to the azimuth, right? Because you're measuring from north to east. So now the bearing of that angle would just be north 60 degrees east. If you have a measurement here, or a line here, you're now looking at an azimuth here, right? There's our azimuth. Our bearing is this angle here, right? So if our azimuth, which would now need to be between 90 and 180 degrees, were 160 degrees is our azimuth, we take 180 minus the azimuth to calculate the bearing. Visually, you can see that, right? That you would take 180 minus the azimuth to calculate your bearing. So that's how you would convert them back and forth. That's why I said I don't think you need to memorize these. I think it becomes very evident when you look at the diagram what you need to do, whether you need to add or subtract 180 from the azimuth and how to make that transition. For bearings, the same applies, just in the opposite direction. So let's get to the meat of why we're doing all this. Ultimately, when you, let me go back to a much earlier photo here, a photo slide. Here we go. Ultimately, when you have a closed traverse, you will typically have an initial meridian. Okay? And you would be told that your initial line of your traverse is at an azimuth or bearing of 30 degrees, 35 degrees, whatever it turns out to be. Well, then what you need to determine is what is the azimuth. Okay, so there's our meridian again. Now what's the azimuth here of C to B? And if I drop my meridian in here again, trying to do this with really straight lines, what's my azimuth of B to A? These should all be parallel, by the way, all these meridians. So now, what's my azimuth of A to E? And if I can get this last one in here straight, yay. What's my azimuth of E to D? So what we're looking at is once we have our initial starting point, we need to calculate the azimuth or bearing of every segment of our traverse. How do we do that? Well, there's a fairly easy way to do that, and it's by calculating with azimuths. When you proceed around the traverse in a clockwise direction, so in this direction, right, that's clockwise, you subtract the interior angle from the back azimuth of the previous course. A back azimuth is simply a reverse azimuth. When your computations proceed in a counterclockwise direction, you add the interior angle to the back azimuth. That sounds very confusing, but it's not so bad. Let's take a look. Okay. This is actually in your textbook, so if that's helpful for you to look at, it is in your textbook. Oh, I thought I had what page it was on, and I don't have that here. So it is in Chapter 4. We are going to do a counterclockwise solution because the math is much easier going counterclockwise than it is going clockwise because you're always adding. If you go clockwise, you're always subtracting. So we're starting at a given point on our traverse. Now this is the same traverse that we just looked at here. This is this same traverse. Our starting point is here at A to B. That's where our given is. There we go. So here is our starting azimuth, start right there. And we're being told that the azimuth of A to B here, so this line right there, is 330 degrees. Okay, so what next? Well, we're proceeding counterclockwise. We're going to add the interior angle to the back azimuth of the previous course. So we have the azimuth of A to B. We now want the azimuth of B to C. So we are going to add the interior angle, there's our interior angle, at B to the azimuth of B to A. That's what it's telling us. Add the interior angle to the back azimuth of the previous course. Our previous course is segment AB. We need our back azimuth B to A, and then we're going to add the interior angle. Visually, what does that look like? Well, here is your azimuth of B to A, and then you add this interior angle here to get the azimuth of B to C. Mathematically, remember that the azimuth and the reverse azimuth are always off by 180 degrees. Since our azimuth is 330, we're going to subtract 180 degrees to bring us back to our azimuth of B to A. So you can see the math is up here and up here. So the azimuth of A to B is 330 degrees. We're subtracting our 180 degrees, giving us an azimuth of B to A of 150 degrees. We're now adding the angle at B, that interior horizontal angle of 120 degrees and 28 minutes, giving us an azimuth of B to C of 270 degrees, 28 minutes. Okay? And you can see from the diagram that that seems to be about right, right? B to C almost looks like it's at 270 degrees, right along that east-west line. Now we would move to the next diagram. So now we know B to C, the azimuth of B to C. It's 270.28. We just calculated that. We now need our reverse azimuth of C to B. So again, we're going to subtract 180 degrees, giving us our azimuth of C to B of 90 degrees and 28 minutes. We're going to add the angle here at C. There's our angle at C. Right here is our reverse azimuth. So we're adding the angle at C of 118 degrees and 37 minutes, giving us an azimuth of C to D of 209 degrees and 5 minutes. And then you just continue around the diagram until you come all the way back to where you started. You'll know if you've done this correctly because when you come back on that very last connection, you're actually going to be calculating your initial given azimuth. So you can see here in this finish check calculation that you're actually calculating back to the azimuth of A to B, which we know should be 330 degrees. If when you calculate back, you do not calculate to the 330 degrees you started with, you have an error somewhere in your calculations, your azimuth computations. The other thing that I need to point out that we'll see when we jump to Chapter 7 next is that this only works once you've balanced all of those interior angles to equal to the geometric required value. Otherwise, you'll be off here as well. So does this make sense? I know it's kind of a lot to throw at you, but again, we only have a short period of time in these live sessions. Yes, you will definitely need to spend some time trying it yourself. And then your book is going to ask you to calculate these both in forward and backward, meaning in clockwise and counterclockwise directions. And it will also ask you to calculate these using bearings as well. The easiest way to do this is to calculate using azimuth in the counterclockwise direction. That is the easiest because the map is the easiest and it's a pattern. Bearings are a little bit trickier. Let's take a look at these. The reason that bearings are a little bit trickier is because there's no pattern. You have to look at each and every angle point individually and evaluate your knowns and unknowns and then calculate accordingly. So this is the exact same diagram we were just looking at. Okay, it's the same traverse with our starting, remember our starting azimuth was 330 degrees. That makes our starting bearing what? If our starting azimuth of A to B, this azimuth here, was 330 degrees, what is, oops, that's an A, what is our bearing of A to B? Yes, exactly. So our bearing of A to B would be north 30 degrees west, right? It would be this angle right here. This is our north. This is our west. So that is A to B. Therefore, B to A would be south 30 degrees east. So you can see here in this initial start that B to A is listed as south 30 degrees east, right? There's that measurement. What we're looking for is this bearing of B to C. So what we know is that this is 30 degrees and this entire interior angle is 120 degrees, 28 minutes. Well, if we subtract out the 30 degrees from the 120, that tells us this angle here And then if we, oh geez, what just happened? Ah, there it is, sorry. And then if we subtract that value from 180, we get the value of our bearing. So you can see that that's what they're doing here. So 180 degrees minus 128 minus this 30 is equal to 89 degrees 32 minutes in this northwest quadrant. So our bearing for line BC becomes north 8932 west. Now you have to take that information and go to the next and start all over again. What do I know? What do I have? What do I need to calculate? So calculating around a traverse using bearings is quite a bit slower and a little bit more cumbersome because you have to keep evaluating every single piece and determining what you need. My recommendation for your homework for this particular chapter is that you start early. It will take you some time, and that you draw a sketch for every single part of every problem. Because being able to see these things graphically like this makes a huge difference in understanding what the values are and where they are on the diagram, and then what needs to be added or subtracted. So I don't believe that this assignment is particularly difficult, but it can be very time-consuming until you get into these patterns and get adjusted to talking in azimuths and bearings. So it is fairly time-consuming, and don't wait till the last minute to get started. Okay? Are there any other questions about calculating with azimuths, calculating with bearings, why we're doing this, how this fits together? Do spend some time practicing this, and hopefully it will become a little bit clearer. No questions? Because we ran through it really, really quickly. Okay, excellent. Yes, definitely practice on your own. I will be sending an email, but I do need to change. Our next live session is scheduled for this coming Sunday morning, the 21st of October. At a minimum, I need to change the time of the session. In all likelihood, I will also be changing the date of that session. So just to let you know that that will be coming shortly. Again, a reminder, I'm going to be at a conference the next few days, but I am available through email for questions. So please get started on this, and then let me know if you run into any problems between now and when it's due. And I'll do my best to help you through email get through some of these. If we need to talk on the phone, we can do that too. I'd be happy to call you from the conference if we need to do that, or over the weekend. So, so that's where we're at. I'm going to go ahead, unless there's other questions, I will go ahead and stop the recording.